Good morning, students. Today is the third class of ring theory, AKNU 5th semester mathematics, paper 5. Now, we are going to the next theorem. Before that, we have to learn some definitions. In the previous one, there is a definition. I have explained that zero divisors of a ring R is said to have zero divisors if A not equal to 0, B not equal to 0, then AB is equal to 0 for all A comma B belongs to R. I have already explained this one. But no zero divisors of a ring. In the above one, zero divisors. And the below one, no zero divisors. There is an opposite meaning is there now. So the definition is also quite opposite. What is that? Here for zero divisors, A is not equal to 0, B not equal to 0, AB equal to 0. For this no zero divisors, there is opposite meaning. A not equal to 0, B not equal to 0 is same. But here AB equal to 0 for zero divisors. Here AB is not equal to 0 for no zero divisors. So students, what is no zero divisors? A ring R is said to have no zero divisors. For any two elements A comma B in R, if A not equal to 0, B not equal to 0, then AB, the product of AB is not equal to 0. And there is another definition, that means another form is there for no zero divisors, that is, if the product is 0, then one of these two, A or B, must be 0. And that means either A equal to 0 or B equal to 0. This is a very important definition for next coming definitions or coming syllabus. That is, the next definition is integral domain. A non-empty set R with respect to two binary operations plus and dot is called integral domain if integral domain is simply noted as I dot D, ID means integral domain. If first one, R plus dot is abelian ring. A non-empty set R with respect to binary operations plus and dot is said to be integral domain if R plus dot is abelian ring. The first condition is abelian ring. The second one is R has no zero divisors. What is the second one? R has no zero divisors. If we observe that previously in the above, that means if we observe that here, a ring R is said to have no zero divisors. If A B equal to 0, then either A equal to 0 or B equal to 0. Or if A not equal to 0, B not equal to 0, then AB not equal to 0 for all A comma B belongs to R. This is the definition for no zero divisors. That means for an integral domain, a non-empty set R must satisfy two conditions. That is, R plus dot is abelian ring, not only ring. It is an abelian ring, and R has no zero divisors. If R satisfies these two conditions, then that R is said to be integral domain. And cancellation loss, just for the reference only, here it is mentioned. If AB is equal to AC, then B is equal to C. We are on land in the previous also. A was cancelled on the left side. Here also, if BA is equal to CA, then B is equal to C. A is on the right side, but it was cancelled, and we got B is equal to C. It is called right cancellation law. These two laws are said to be cancellation laws. These are the definitions. And there is a theorem for this, that means basing on the land definitions. What is the statement is, the theorem 3 is, a ring R has no zero divisors. A ring R has no zero divisors if and only if cancellation loss holds. That means R has no zero divisors if and only if cancellation loss holds in R. This is necessary and sufficient condition like theorem. What is necessary condition? We want to take no zero divisors, we have to prove cancellation loss holds. What is sufficient condition? We have to take cancellation loss holds, and we have to prove R has no zero divisors. Students, are you understanding that? What is that? Necessary means we have to take left and we have to prove right. What is sufficient condition means we have to take right, we have to prove left. Okay. There is another type of questioning is there in the question paper. That is, what is that is, if R is an abelian ring, then R is integral domain if and only if cancellation loss. If R is abelian ring, then R is integral domain if and only if cancellation loss holds. If you observe that R is abelian ring is the common part for the necessary and sufficient condition for these two parts. So we are writing that given R plus dot is abelian ring for the proof. Proof in 2 pages. Proof of page 1 of the 2 pages is, I am starting with the proof by giving R plus, or given that R plus dot is an abelian ring. First we prove the necessary condition. What is the necessary condition? I told you earlier that we have to take left, we have to prove right. What is left? Given R is, suppose R is integral domain, we have to take R is integral domain. We have to prove cancellation loss holds. If we go to the first statement of this theorem is R has no zero divisors is left, right is cancellation loss holds. So we have to take left, that is R has no zero divisors. So I am taking that suppose R has no zero divisors or R is integral domain, whatever it may be that. R has no zero divisors. What is the meaning of R has no zero divisors? I am writing here the definition, that is if AB equal to 0, then either A equal to 0 or B equal to 0. If you go to the back, the definition of no zero divisors is 2 types is there. I am taking the first type. Are you observed it? Okay, right. I taken the first definition, that is the first type definition. Okay, what we have to prove? We have taken no zero divisors. We have to prove cancellation loss holds. That means we prove that cancellation loss holds in R. For that, I am taking that A is only a non-zero element and B comma C are elements in R. A is non-zero and B and C are elements in R. Now I am taking that let AB is equal to AC. AB is equal to AC. That AB minus AC equal to 0. You can observe that AB is equal to AC and the next step is AB minus AC equal to 0. Now, by the previous theorem 1 of the third bit, if you observe that in the theorem 1 of third bit, A into B minus C, I am writing by using the theorem of third bit or by the distributive law. A into B, AB minus AC can be written as A into B minus C is equal to 0. Here, it is looking like AB equal to, this total B minus C considered as B. AB is equal to 0. It is looking like A into B is equal to 0. But R has no zero divisors. That means if AB equal to 0, then 1 of AB is 0. That means either A equal to 0 or B equal to 0. Similarly, if we apply this condition for this one also, in these two multiplications, one of the multiplication is 0. That means either A equal to 0 or B minus C equal to 0. But we have taken that A is non-zero. Is it right? Are you following the cursor? Yes. You can see that A is not equal to 0. That means the only remaining part B minus C must be 0. Because one of these two products must be 0. But A not equal to 0. That's why B minus C must be 0. B minus C equal to 0 means B is equal to C. I have taken that AB is equal to AC. But the result is B is equal to C. That means left A was cancelled. Are you observed that? Are you observed the first line and the last line? AB is equal to AC we have taken, B is equal to C. What were vanished? Left hand side A were vanished. Is it right? That means left cancellation law is successful. Similarly, we prove the right cancellation law. What is that? Similarly, we prove that BA is equal to CA, then B is equal to C. Therefore, we say that cancellation loss holds in R. That means, if we taken that in an integral domain, cancellation loss holds. We can use this statement. This is also a statement. Sometimes the question will be asked is like that also. For the necessary condition in an integral domain, cancellation loss holds. This was the statement. You can get in the examination. You may get in the examination. So at that time, you can write the answer of this theorem only necessary condition only. So we proved that if R has not zero divisors we have taken, then cancellation loss holds. Now we are going to the sufficient condition. That means right to left. What is right? Cancellation loss holds. We have to prove that R has no zero divisors. If we go to the second statement, what is right? Cancellation loss holds. We have to take cancellation loss holds. We have to prove R is integral domain. That is sufficient condition. Suppose cancellation loss holds in R. We have taken right side. Are you observed that? Suppose cancellation loss holds in R. What we have to prove? R has no zero divisors. R has no zero divisors. What is zero divisors? No zero divisors definition we have learned. By using this, I am taking that A is a non-zero element and B is an element in R, such that AB equal to 0. I am taking the product is 0. Then what is the definition of zero, no zero divisors? If we take product is 0, then either A equal to 0 or B equal to 0 will be happen. So I am taking that AB equal to 0. AB is equal to 0 can be AB, LHS part was written same, is equal to 0 can be written as A into 0. It can be written by theorem 1 first bit. 0 may be written as A into 0. If you observe that there is a small mistake, I will clarify. Okay, students. AB is equal to 0 may be written as A into 0. By left cancellation law, because we have taken suppose that cancellation loss holds. So by using that cancellation law, by left cancellation law, A is cancelled from left side. That means B only remains here, LHS part, and RHS part 0 will remain because A was cancelled. B is equal to 0. Okay, students, we have taken that AB equal to 0 and B equal to 0, we have got it. And A is not equal to 0. In that product, one of the element must be 0. But A is not equal to 0, we have taken. So the one element, another element B is 0. That's why R has no zero divisors was proved. Therefore, R is integral domain. How we can say that only R is integral domain? With that element only R has no zero divisors, with that condition proving. If we observe that in the first one, R is abelian ring. For the common part, given R is abelian ring. R was abelian ring condition was already given, and R has no zero divisors was proved, or it was proved now. So with these two conditions satisfaction, we say that R is an integral domain. We have taken cancellation loss force, we prove that R is integral domain. That means RHS to LHS condition is also over, that is sufficient condition was satisfying. So the theorem is over. Note, in an integral domain, cancellation loss holds. Previously I explained that sometimes it may be given like that. The question is given like that in the university question paper. What is that? In an integral domain, cancellation loss holds. What is the proof of this statement is, you can write the necessary condition proof of this theorem 3. I have already explained the previous one. Okay, right. Next, we go to the definition division ring. A non-empty set R with respect to two binary operations plus and multiplication dot is called division ring if the first bit R plus dot is ring only. R plus dot is ring. The second one is R has unit element. Unit element means multiplicative identity. What is the multiplicative identity? 1 must be in R. That is, if we write the multiplicative identity law, for A belongs to R, there exists 1 belongs to R, such that A into 1 is equal to A is equal to 1 into A. This must be satisfied. And the third one is, every non-zero element in R has multiplicative inverse. It is nothing but a multiplicative, that means inverse law with respect to multiplication. It is a inverse law with respect to multiplication. What is that? For 0 is not equal to A belongs to R. A is a non-zero element in R. There exists A inverse belongs to R such that A inverse is equal to 1 is equal to A inverse A. Okay? Right. The first one is R plus dot is ring. The second one is R has unit element. The third one is every non-zero element in R has multiplicative inverse. If R satisfies, a non-empty set R satisfies with these three conditions with respect to the operations plus and dot, then that R is said to be division ring. Okay, right? Next we go to the definition. Field. A non-empty set R with respect to two binary operations plus and dot is called field if this is also it. In this definition also we have 3 bits. What are they? R plus dot is abelian ring. What is the difference between? In the previous definition, the first bit is R plus dot is ring. In this definition, in this field definition, the first condition is R plus dot is abelian ring. The next one condition is the same as the division ring. R has unit element, R has unit element. The same condition. The third one is every non-zero element in R has multiplicative inverse in R, which is also learned in the division ring definition. This is also same. Second and third are same for the division ring and field. What about the first one? There is a small difference. What is that? In the division ring, R plus dot is ring. In the field, R plus dot is abelian ring. What is the main difference between these two definitions? Abelian is the only difference. You can observe that. In the field, abelian is the extra one. Okay, that? Okay, are you following? Division ring also satisfying 3 bits. Field is also satisfying 3 bits. In these two definitions, the first bit is difference. What is the main difference? R plus dot is ring in the division ring. R plus dot is abelian ring in this definition field. What is the main difference in these two? Abelian. What lost in division ring? We don't have abelian law. But in the field we have abelian law. That means if a division ring with abelian law is also satisfies, then that is a field. Is it right? That means an abelian division ring is field. We can write like that. An abelian division ring is field. Dear students, today you all want to study the definitions well, because in today's class we have discussed the definitions, important definitions. No zero divisors of a ring. That means ring has no zero divisors, and the main one is integral domain. And now we discussed that division ring and field. These definitions are very important, because in further theorems it will be very useful for us to understand the further theorems. That is, main definitions are integral domain and field. You must learn these two and understand well. That's why I am closing this class with this syllabus only. First of all, I will post these topics in the PDF format in your WhatsApp group. So all of you want to note down in your notes, and I will examine that whether you are. I will examine your notes in the coming class. So students, everyone want to write the notes regularly. It will give you the good habit, and it is a good habit for you. It gives you a long benefit. So students, all of you want to follow my guidelines, and have a good day. Thank you. We will see in the next class, in the tomorrow's class. Don't miss the classes, okay? Because it is a theory one. Everyone must continue each and every class, and everyone must follow the classes regularly. And you can see these classes in our channel. That is, KHL channel is there, and KHL Degree College channel is there. In that one also you can view these classes in our YouTube channel by downloading it, because some students, in the rural people students, some students doesn't have the net facility properly. That's why we are posting all these YouTube videos in the YouTube channel by the guidelines of our Honorable Vice Chancellor. So everyone must follow that guidelines, and we will give success and good result to our university. Thank you.